Hey everyone. Today I actually have a little bit of a demonstration for you. I'm actually going to be setting up the activity that I'm asking you to do next. And it turns out that directly measuring the frequency of a sound is pretty hard. Most sounds that we care about as humans have frequencies in the hundreds or thousands of hertz. So you either need to be really resourceful and clever about how to measure something that's, vibrating or oscillating hundreds or thousands of times per second, or you need to rely on modern electronics, which can do it pretty easily, but that's kind of cheating. Um, but measuring wavelength is actually really easy to do. All you need is a tube. So right here I have a graduated cylinder. The cylinder is filled with water, and inside the graduated cylinder I have a metal pipe. The metal pipe is hollow, um, and by submerging one end of the pipe in the water, I create an air column um, with one closed end. The water basically acts as a closed end of this pipe or this tube, and one open end. Um, and the reason why I've set it up like this is because by moving the cylinder into and out of the water, I can adjust its length. If I want to determine the wavelength corresponding to a particular tone or frequency of sound, all I need to do is increase the length of that air column until I find resonance. So right here I actually have a tuning fork. Tuning forks are created to have a particular resonant frequency so that when you cause them to vibrate, like hitting them on a big piece of rubber, they make a ringing sound. And this ringing sound is very close to a pure tone, a specific frequency of sound. So if I take this tuning fork and I hold it up to my tube over here, not much happens. But as I change the length of this tube, at a particular length, you notice that the sound gets much louder. And what we've done there is we've found resonance. Let me do it again. And you'll notice, by the way, you don't hear the sound very well until you reach that particular point. And then if you go past it, the sound goes away again, or it gets softer. Oops. So since this is the shortest, when it was about this high, let me actually do it again. So it's right there. This is the shortest length of an air column that gives us resonance. I know it wasn't here. In principle, you could say, oh, what if there was resonance if we could make it shorter? I know that it's actually not. So this is the shortest length of the tube that gives us resonance with this particular frequency of sound. That means that the wavelength of sound produced by this tuning fork is the fundamental of a pipe with a closed end and an open end of this particular length. Since for an open pipe like this, the fundamental wavelength is equal to 4 times the actual length of the tube, that means all I need to do to find the wavelength of the sound produced by this tuning fork is to measure the length of the air column. If you were to actually do this measurement, be aware that as you lift the tube out of the water level changes. So you can't just measure where the water level was and use that to measure your length. You have to actually measure from where the water level is when your tube is at the appropriate length. Since the frequency and wavelength are related to each other by the speed of sound, or by the speed of a wave, if you know either the frequency or the speed, you can use one of them to find the other one. Or you can use this experiment to find the other because you can measure the wavelength of the sound in air. So again, this tuning fork vibrates at a particular frequency. In this case, this tuning fork is a 512 hertz tuning fork. I don't know if you can see that. Yeah. Which actually corresponds to the note middle C. So you could use this to tune an instrument. In fact, that's why they're called tuning forks. That's what they were used for originally. A tuning fork was designed to help you tune things to a specific note. If we wanted to get more precise, we could repeat this experiment different times by varying different things. For example, this tuning fork is a 384 hertz tune corresponding to the note G. So I could find the position of the tube that gives us resonance for this tuning fork. Which is right there. And you might notice that this length is bigger than the length that we had for the 512 hertz sound, which makes sense because the G note has a smaller frequency, which means it has to have a higher wavelength than the middle C note. So the lower frequency tuning fork produces a longer sound wave when it pushes against the air. I can also try to find different harmonics. So for example, I can get resonance more than once. I get resonance when I find the length of this tube that's equal to 1/4 of the wavelength of the sound produced by this tuning fork. But I would also get resonance if I make the length long enough so that I'm actually looking at one of the higher harmonics of the tube. In this case, you'll notice that we don't find it. The reason for that is that this tube isn't long enough. In order to have resonance for the next harmonic course, or rather, in order for the wavelength that I'm making to be the second harmonic, I need a longer tube because the fundamental would be a longer wave, meaning I need a longer tube. So what I can do to demonstrate this is I can use my phone because you can use online tone generators or apps that generate pure tones. And I can play a higher frequency sound, or not. Hey. Why are you not working? You were just working. There we go. So this is kind of an obnoxious sound, but it's a higher frequency sound. In this case, I've chosen 756 hertz for no particular reason. But I do know that it is high enough frequency, which means it produces a small enough wave that I'll be able to not just get it in as the fundamental wavelength of my tube, but I'll be able to fit sort of more of the wavelength in and find a second harmonic. So let's look for them. So here's the first. So this length corresponds to the fundamental, or rather the wavelength of the sound I'm generating is the fundamental of this length tube. And right about here is where the sound I'm generating corresponds to the second harmonic of a tube of this length. I'm hopeful you'll be able to hear that between my microphone being able to pick up the sound well and your speakers being able to play it back well. It might be a little bit hard to hear. Let's actually see if we can do that again. Oh, that's obnoxious. I have to reload the page every time to make it work. Oh, here. No, this is as loud as my phone will go. But again, let's do it again. So right there, you can hear that we've reached resonance. And right here, we have it as well. It's hard to pick up, though. These higher frequencies can sometimes be difficult to hear well. And in this case, it's complicated because the phone is... I'm actually not entirely sure where the sound is coming from. But anyways. So the second... Nothing about the sound I'm creating is changing. It's just that in the first case, the sound wave corresponds to the fundamental of a shorter tube, but it can also correspond to a higher harmonic of a longer tube. And so you guys are going to basically be doing this experiment. I encourage you to do it yourself physically if you can find the materials. You don't need a graduated cylinder. You can use any deep enough container to hold enough water. You can use an online tone generator, so you don't need to have randomly in your home tuning forks. You can also just use a musical instrument, and you can use a tuner, so either like a physical device that lets you figure out whether something is in tune, or you can use your phone, and you can measure the frequency of the sound that your musical instrument makes, and you can actually use your musical instrument to create the sound that you're using to generate this resonance. In terms of the tube itself, the more rigid the tube, the better. Metal and glass are ideal. PVC can work. It might be a little bit harder to hear the sound. Cardboard might work if you're really lucky, but the softer the material, the more deformable the material is, the better it absorbs sound, which means you're not going to hear this resonance as clearly. So if you can find a nice rigid tube like this, it would work. If you want to use frequencies that aren't obnoxiously high-pitched or really low-pitched, you're probably going to want a tube that's within the 1 to 3 foot range. 3 foot would be pretty big and excessive for most purposes. This, I think, is... actually, I have no concept of length. I don't know what this is. Maybe it's 2 feet, maybe it's 1.5 feet or something. I don't know. But on the order of a couple feet is about what you'd want ideally. So hopefully this helps, and I hope that many of you get to try this for yourselves. Things don't need to be perfect. If you have kind of a janky setup, like for example, I stole this graduated cylinder from school before I left, just in case. But you could also use like a vase or a pitcher of water, or even a sink or a bathtub. As long as you can find an appropriate tube to submerge in the water, all that really matters is the depth that you can make. All right, I will see you next time.